Greetings, pre-calc students. It's time for another action-packed lesson, this time on lesson 9-8, powers and roots of complex numbers. All right, look at this kind gentleman. His name is Mr. De Moivre. De Moivre. Say that a few times. De Moivre, French mathematician who came up with this famous theorem, which we're going to talk about today. Notice one of the other interesting parts about his life is that he could predict the day of his own death. So that was pretty cool, I guess. All right, here is the famous De Moivre's theorem right here. This enables us to find both powers and roots of complex numbers. If you look at this, notice that your polar coordinate has to be in polar form, obviously. So sometimes when they're in rectangular form, like we did last lesson, we'll try to convert it back to polar form. And a little bit like we did with multiplication and division, notice what happens here. The r value is raised to that power, and the angle is multiplied by that power. So make sure you write this down. Very important. We'll be using this whole lesson. Now let's take a look at some examples and see how this works. So there we have the the rectangular or a plus bi form, 1 plus I, and we're going to take it to the 5th power. Now that would be pretty tough to do, a real pain to multiply that out 5 times. So here's where De Moivre's theorem is really going to help us out. Once again, the first thing we want to do is convert this into that polar form. So remember, to convert it to polar form, we need r and theta. So with our particular coordinate here, it's over 1 on the x-axis, 1 on the y-axis, so we have a 45-45 right triangle. That means that our hypotenuse, or r value, is the square root of 2, and theta is 45. So we can write that as square root of 2 cosine 45 plus I times the sine of 45. Now when we take this to the 5th power, make sure you write all these steps down because they're a little confusing. We take that r value to the 5th power, and then we multiply the angles by 5. So notice what we get, and we can substitute a value for the cosine of 225 and the sine of 225 and use our distributive property here, so we eventually end up with that particular polar coordinate there, -4 plus 4i. Now we can also use De Moivre's theorem to help us find roots of complex numbers. And we'll do another example here. This is kind of tough, so just try to bear with us and see what you can do. We'd like to try to find the cube roots of -8i. And this seems kind of weird. Can you think of a number that you can multiply by itself 3 times and get -8i? Well, that's why we're going to go through this formula. Once again, we want to write it in trigonometric form, or r and theta. No triangle is needed here because it is right on the x-axis, the y-axis. So it's the coordinate 8, 270. So we're going to do this backwards. Now we have the 8, 270. We're looking for values that we can take to the 3rd power that'll give us that. So we set our r parts equal to one another. So r to the 3rd equals 8. And then we say that 3 theta is going to be 270. So we can solve each of those down a little bit. R, of course, is going to equal 2, and theta is going to be 90 degrees. That's 270 divided by 3. And where did this 120 come from? Well, just like we divided 270 by 3, we have to divide 360 by 3. So we are going to have 3 answers. Those are the cube roots. And we need those because we need those 3 particular answers there, so we keep adding 120 onto each of these angles there. We could convert them to a plus bi form, but we won't do that. Alright, here's a couple of examples for you to try here. Again, this is going to be kind of tough, but see if you can slog through it a little bit. Again, the key thing is make sure to start out by writing them in polar form. You can use that abridged polar form, of course. Here's the answers for those. As you can see. And in conclusion here, remember, it's not the D line, it's De Moivre. We'll talk to you guys on Monday. Have a great weekend.